12 months and comes at 50,000. So in the mentorship plan, we have personalized guidance, live out clarification sessions, and also provide you with notes. Then you can also get 20% additional discount if you use my promo code as displayed here on the screen. Then introducing you a little with the internal exam marathon series. So this series has been specifically designed to target your university exams which are approaching very soon. So we intend to take a quick revision of all the important topics and frequently asked questions. Then apart from that, volatile facts will be quickly revised. Multiple choice questions will also be dealt, all of which is done to assure you top-notch grades in your exams. Okay. So talking about enzyme inhibition, that's the topic for today's class. So enzyme inhibition, it is a very important topic. And not just like for biochemistry, you get direct questions like you might be asked like describe a certain type of inhibition, like competitive inhibition, non-competitive something. Or maybe in a long answer question, you might get asked to describe all of them. But apart from that also, it has application-based questions as well. For example, when you study pharmacology and all, you will see that your drugs, they're basically based on this phenomena. So it becomes all the more important. So that's the scope for today's class, that is enzyme inhibition. So they are classified into different types of inhibitions. So there are main 6 types of enzyme inhibition. First being the competitive inhibition, the non-competitive inhibition, uncompetitive inhibition, suicide inhibition, feedback inhibition, and the most important one, allostatic inhibition. I'm sure you're familiar with this term. This is nothing new because all through metabolism and regulation of the key enzymes, we've been hearing so and so is an allostatic activator of such and such enzyme, or this is an allostatic inhibitor of all that. Like acetyl-CoA is an activator of pyruvate carboxylase and all. So now we're going to study the mechanism, that what is going behind the scene of all that, okay, when we make those statements. Okay. So let's begin with competitive inhibition. So inhibitor and substrate are structural analogs of each other. So in competitive inhibition, your inhibitor and your substrate, they are structural analogs. Okay, so they look similar structure when it comes to structure. For example, if your substrate looks something like this, it's like a triangle. So your inhibitor is also going to look something like this. Okay, so they are structurally similar. They look similar. That is why the enzyme gets confused between the inhibitor and the substrate. And also, your inhibitor binds to the same site where the substrate binds. Okay, firstly, your inhibitor is going to resemble your substrate, and secondly, it is also going to bind at the same active site where your substrate is going to bind in the enzyme. For example, let's suppose this is an enzyme. Okay, this is an enzyme and this is the active site. And this is your substrate. So your substrate was supposed to bind in this active site of the enzyme, and as a result of which the reaction was going to take place and the product was supposed to be formed. Now what happens? There is a structural analog, but which is not the substrate. Okay, it is an inhibitor, but it looks like the substrate. This, but it is an inhibitor, and it is structurally similar to the substrate, so it is going to compete on the same site on the enzyme as the substrate. So if this inhibitor comes and binds to the substrate, what will happen? This enzyme will be inactivated, inhibited. Okay, so this is your enzyme. When the substrate binds to the enzyme, what happens? Enzyme substrate complex is formed, ultimately leading to the formation of enzyme and products. But what happens when to this enzyme, your inhibitor comes and binds? So what is formed? Enzyme inhibitor complex is formed and there are no products being formed. No products. Okay. Moving forward, it says that your competitive inhibition, it is reversible. Okay, so it can be reversed. Okay, the binding is not permanent. Inhibition can be overcome by increasing substrate concentration. More substrate will get a chance to bind. So here, let's take this example, okay? The diagram that I've drawn. So if you increase, now you have this inhibitor, but what happens if you increase the concentration of the substrate? Now see, you have so many substrate and you just have one inhibitor. So what happens? The chances of the substrate binding to the enzyme, you've increased those chances, okay? So by increasing the substrate concentration, you can overcome this inhibition, which is being caused by this inhibitor. Okay, so by increasing the substrate concentration, although you are overcoming this inhibition, but what do you increase? The Km increases. Okay, remember what was Km? It was that substrate concentration at which the velocity was half of the maximum. So earlier, let's imagine it was taking place. Let's suppose two substrates were there, and the Km was being reached. Now you need to add like 6 substrates. So you're increasing the substrate concentration. So what is happening? Increasing the Km, but the Vmax remains constant. Okay. So this is like only for explanation purposes. I'm telling you 4 and 5. Otherwise, your concentration, everything, it is in moles. Okay. So I'm not using the units because this is only for explanatory purposes. Okay. Now here is the graph. The graph is very important. Now see, you have increased the Km. Earlier the Km was here. Let's imagine it was at 2 mg per real. Now the Km is here. Okay, so you've increased the Km, but the Vmax, as you can see, this red line is when inhibitor is used. Inhibitor present, okay? And this blue one indicates without inhibitor. Okay. So you see the Km has increased, but the Vmax remains same. And this is the line we were double reciprocal plot. So here also you can see this is when you use the inhibitor, and this is sans inhibitor, that is without inhibitor. So the Km increases. You can see here it has shifted from here to here. The Km is increasing, and your Vmax, you can see it remains same. So that was about competitive inhibitor. Now you see the application of competitive inhibition. So drugs are the most commonly used competitive inhibitors. You see? Now statins, if you remember when we were doing cholesterol synthesis, we already studied statins. Statin inhibits HMG-CoA reductase. So this was the enzyme involved in cholesterol synthesis. And this statin is a structural analog of HMG-CoA. So I'll revise it a little. What was happening? HMG-CoA, it was being acted upon by HMG-CoA reductase. The valonate was being formed. And then ultimately, what was being formed? Cholesterol was being formed. Now in hypercholesterolemia, that is when the cholesterol level is high. So the body should not be producing more cholesterol, okay, because it will only aggravate the condition. So what happens? Drugs are given, that is statins are given in that case. And what do statins do? They inhibit this enzyme HMG-CoA reductase. So what will happen? Your cholesterol synthesis is decreased. And this was what I had already told you, but now you know the mechanism of action. Why? Because your statins, they are structural analogs of HMG-CoA. So instead of your HMG-CoA going and binding to the enzyme HMG-CoA reductase, what happens? Your statins, they bind to HMG-CoA reductase and bring about inhibition of this enzyme. Okay. So that is the mechanism of inhibition or mechanism action of statins basically. How do they inhibit HMG-CoA reductase? Now talking about dicomerol, it inhibits vitamin K epoxide reductase. This also we've also studied when we were talking about vitamin K during our vitamin series. So your vitamin K epoxide reductase, it was changing the hydroquinone form of vitamin K into the epoxide form. And then the epoxide form was being changed into the hydroquinone form, and this was brought about by this enzyme vitamin K epoxide reductase. Okay, and the inhibition of this enzyme is brought about by dicumarol. Methotrexate also we have spoken about this, that it was inhibiting your dihydrofolate reductase. And what was the function of dihydrofolate reductase? It was involved in production of active form of folic acid, that is tetrahydrofolic acid. So your tetrahydrofolic acid was not being formed. Then succinyl-CoA inhibits acetylcholine esterase. Okay, so these are some of the examples of the drugs that are most commonly used as competitive inhibitors. So with this, we come to the end of competitive inhibition. So we've done this. Now moving on to non-competitive inhibition. Okay. Non-competitive inhibition, the enzyme has an active site to which a substrate binds, and the inhibitor binds to another site which is not the active site. Now you see the contrast between competitive and non-competitive. There, the inhibitor and the substrate, they were competing for the same site. Okay, therefore the name competitive inhibition. But here what is happening? Your enzyme, you can see here in this diagram, this enzyme has an active site where the substrate is supposed to bind, and it has another site other than the active site, and this is the site where your inhibitor is going to bind. Okay. Now the substrate and the inhibitor are not structural analogs. So this is also in contrast to competitive inhibition, where they were structural analog of each other, and both the points go hand in hand. Okay, since they're binding to the same site, so they need to be structural analogs. And here the binding sites are different, so it does not matter whether they look or resemble each other or they don't. Okay, so here in this case they don't. So you see the inhibitor is binding to a different site, some other site present on the enzyme, and not on the active site. Okay, now let us see the consequences of this binding of the inhibitor to the enzyme. So Vmax decreases, but Km remains same as the inhibitor does not interfere with the enzyme substrate binding. Okay, so your Km, the affinity between the substrate and the enzyme, is not going to be altered because it is nowhere hindering the substrate binding to the enzyme. Okay, because your inhibitor is binding to an altogether a different site. Okay, so your Km remains same, but Vmax is going to decrease because inhibition is going to happen. So what has happened? The velocity of the enzymatic reaction is going to decrease. The substrate will bind to active site, but as long as the inhibitor is bound to the other site, products will not be formed. So your Km, the affinity, the binding of the substrate in the enzyme remains unaltered. Your substrate is going to bind to the active site, but what is happening? As long as the inhibitor is present in the other side, the products will not be formed. So your velocity Vmax decreases. And these are the graphs for non-competitive inhibition. So you can see your Km remains same in both the cases, but your Vmax, it is going to decrease. From here, the Vmax has reached here. This red one indicates when inhibitor is used, when inhibitor is not present. Inhibitor absent. Okay. So you see, so Vmax decreases and Km remains same. And this is in the Lineweaver-Burke plot. You can see your Vmax is going to decrease. Since this is a reciprocal plot, so it is going to shift upwards. Okay, so Vmax decreases, but Km remains same. Okay. Now it says the inhibitor can bind to the enzyme as well as the enzyme substrate complex. Okay, so in non-competitive inhibition, your enzyme is going to bind to the substrate and form enzyme substrate complex. So your inhibitor is capable of binding to this enzyme substrate complex and form EIS, and also it can bind to free enzyme and form inhibitor enzyme complex. Okay, so the inhibitor can either bind to the enzyme, free enzyme, or it can also bind to the enzyme substrate complex. Okay. Now, most of the non-competitive inhibitors are irreversible. This is again in contrast to competitive inhibition. So you have to compare the two, okay? Keep listing down the differences in your mind. Firstly, they're not structural analogs, non-competitive inhibitors. They bind to different sites, unlike the competitive inhibitors. Then secondly, the competitive inhibitors, the inhibition can be reversed, but here non-competitive inhibitors, they are irreversible except for the action of trypsin inhibitor on trypsin. So this is the exception. So if you remove trypsin inhibitor from the environment, from the medium, what will happen? Trypsin will be activated again. Most of non-competitive inhibitors, they are poisons. Like cytochrome C oxidase is inhibited by cyanide, known as cyanide poisoning. Glyceraldehyde triphosphate inhibited by iodoacetate. We've done this in glycolysis. You see, enzymes are really important. Maybe directly, you'll not be you'll not be asked like define enzymes or something, but they have an application, throughout metabolism, throughout regulation, throughout while you're studying drugs. Okay, enolase is inhibited by fluoride. Again, we've done this in glycolysis. Very important that you keep revising the previous chapters that we've already done. Alpha ketoglutarate dehydrogenase, it is inhibited by arsenite. This has been taken up in TCA. Aconitase, it is inhibited by fluoroacetate, also involved in TCA, this enzyme. Okay, so that was about non-competitive inhibition. Now moving forward to uncompetitive inhibition. Inhibitor does not have any affinity for the free enzyme. Now, are you able to appreciate the difference between non-competitive and uncompetitive? Your non-competitive inhibitors, they were able to either bind to the free enzyme or to enzyme substrate complex. But here the inhibitor cannot bind to the free enzyme. It binds to the enzyme substrate complex only, okay, and not to the free enzyme. Now, Vmax decreases, Km decreases. Both your Vmax and Km is going to decrease. Unlike non-competitive inhibition, where your Km was remaining same. So, an example is inhibition of placental alkaline phosphatase by phenylalanine. So, you can see this line here, it represents when the inhibitor is not present. And this here, you can see Vmax is also decreased and Km is also decreased. This is a reciprocal plot. So when you shift upwards on the graph on the scale, so it is actually decreasing because since it is reciprocal 1 by V. Similarly, this is on the negative scale, negative axis. Therefore, as you move away from the zero, it is a smaller value, so it is going to decrease. Now, moving forward to suicide inhibition, again important. You can be asked about suicide inhibition in short notes. Also known as mechanism-based inhibition. The original inactive inhibitor, which is a structural analog of the substrate, gets converted into a potent inhibitor by using the enzyme's own reaction mechanism and inactivates it. So it is trying to say that here in suicide inhibition, your original inhibitor, it is inactive, okay? So when it is inactive, it is not potent, it is not acting. But what happens when it comes in the vicinity of the enzyme or binds to a specific site of the enzyme, what happens? It is transformed into a more potent inhibitor by causing changes in the enzyme's active site, conformational changes, because of which it is able to bind permanently and irreversibly to the enzyme, becoming a potent inhibitor and inhibiting the enzyme. Okay, so the original inhibitor is inactive and it resembles the substrate, but it gets converted into a potent inhibitor by the enzyme itself, okay, and inactivates the enzyme. This newly formed potent inhibitor binds irreversibly to the enzyme. This is a special type of irreversible inhibition. Now example, like your allopurinol, it inhibits xanthine oxidase. But what happens when allopurinol binds to xanthine oxidase? It is converted into alloxanthine. And this alloxanthine is actually that potent inhibitor which irreversibly inhibits the enzyme xanthine oxidase. Okay. Now, difluoromethyl ornithine, it inhibits ornithine decarboxylase. It is used in sleeping sickness, and this ornithine decarboxylase, it is involved in polyamine synthesis. Now moving on to feedback inhibition. So end product inhibits the first enzyme. It is known as end product inhibition. Let's say, for example, there's a pathway going on. A is changing into B, B is changing into C, C is changing into D. And this is brought about by enzyme E, F, and G. So it is saying the end product, in this case D, it inhibits the first enzyme. That is here in this case E. So this is known as end product inhibition. That is your product, last product, end product is going to inhibit the first enzyme in the pathway. So this is end product inhibition. Increase, for example, increased mevalonate inhibits HMG-CoA reductase. So you see HMG-CoA, it was changing into mevalonate. The enzyme was HMG-CoA reductase. So when mevalonate is increased, it inhibits this enzyme. Okay, so the end product, which is mevalonate, it is inhibiting the enzyme. Okay, and what is feedback regulation? The end product is not acting on the enzyme. Instead, the end product will inhibit the gene that transcribe and translate the enzyme. Okay, so here in this case, this was feedback inhibition since your mevalonate was inhibiting HMG-CoA reductase. Okay, but what happens when this mevalonate is going to act on the genetic level? Okay, see here, if there is enough of dietary cholesterol, then this decreases binding of steroid regulatory element binding protein at genes that synthesize HMG-CoA reductase. So you're trying to decrease the production of the enzyme that is HMG-CoA reductase in itself. Okay, the mevalonate is not inhibiting, it is not acting at the protein level, but rather at the genetic level that the synthesis of the enzyme in itself is reduced. Okay, so leading to decreased expression of genes that synthesize HMG-CoA reductase, which is the late-limiting enzyme in cholesterol pathway. So that is the difference, and we've already taken this difference when we were talking about cholesterol synthesis. And again, when we study heme synthesis, then also you'll study about feedback regulation. Okay. So what is the main difference between feedback inhibition and feedback regulation? In feedback inhibition, the end product is acting at the protein level. It is inhibiting the enzyme. And at feedback regulation, what is happening? It is happening at the genetic level. There is decreased expression of the genes that are going to synthesize that particular enzyme. Okay. So we've taken all the inhibitions. What is left is now allosteric inhibition. So allosteric inhibition, I'll take it along with regulation of enzyme activity. So another very important topic, that is regulation of enzyme activity. Now you can regulate the enzyme activity by either regulating the quantity of the enzyme or by regulating its quantity, quality, or catalytic activity. So there are two types of regulation. One is either you control the quantity, the amount of the enzyme that is synthesized or produced. And the second is that you control its function, you control its quality or its catalytic activity. Okay, so talking about the quantity first, quantity regulation. So you control enzyme synthesis, like I said. Okay, how much enzyme is produced? Okay, if you decrease the production, obviously the amount of enzyme in itself is less, the pathway will not take place. Okay, or if you want to enhance the reaction, you can increase the synthesis or the production of the enzyme. Okay, so that is one way that you regulate the quantity. Okay, if you want to build a wall, so you increase the number of laborers, so obviously what will happen, the time taken to build that wall will be enhanced. Okay, so that is how you increase. Or if the wall is like already finishing its end and you don't need that many labors, so you can decrease the number of labors. Okay, so that is like increasing or controlling the synthesis or the quantity. Now it is brought about by induction and repression mechanism. By the help of an inducer or repressor, structural gene for a particular enzyme can be inhibited or stimulated, thus controlling the synthesis of that enzyme. For example, in the previous case, like we spoke, taking the example of HMG-CoA reductase. So you were decreasing the expression of the gene that was coding for HMG-CoA reductase. So ultimately what was happening? HMG-CoA, the quantity of which was not synthesized. And ultimately what was happening? The cholesterol synthesis was being decreased and your cholesterol levels were being controlled or decreased. Another example is of ALA synthase. This is an enzyme in heme synthesis. If the body is not having enough heme, so now here the body does not have enough heme, so structural genes for allosynthase will be active. Okay, so the genes that are synthesizing allosynthase, they will be activated. Okay, thus more allosynthase is produced, leading to more heme synthesis. So this is an example of activation, that is induction of the structural genes for allosynthase, and that was the previous one was an example of repression of the structural genes for HMG-CoA reductase. Okay, so that is how you bring about regulation, by controlling the quantity of the enzyme synthesized. Now, talking about the quality or the catalytic activity, it includes allosteric regulation and covalent modification. So allosteric regulation is very, very important for your short notes, for your long answer questions. Apart from that, for understanding the regulation mechanism of various metabolic pathways, for their inhibition, activation of the key regulatory enzymes and everything. It is important, like directly also and in a flight form also. So let's begin with allosteric regulation. Allosteric enzyme is an enzyme whose activity in the catalytic site is modified by the presence or absence of a modifier or an effector in allosteric site. So this statement means that, let's suppose this is an enzyme which says allosteric enzymes are those enzymes whose activity in the catalytic site. Let's suppose this is the catalytic site or the active site. So the activity of this enzyme in the active site, it is going to be defined by what? It is going to be defined by this allosteric site. It has another site which is known as allosteric site. So, and in the allosteric site, what is present? A modifier, also known as effector. So a modifier and effector is going to be present or either absent in this site, and this is going to define its activity of the active site. Okay, so that is an allosteric enzyme for you. So your allosteric enzyme have two sites. One is the catalytic site and other is the allosteric site. So such enzymes can act only if the modifier is present. Okay, so if the modifier is not present here in this allosteric site, this enzyme is not going to act. So allosteric site has, enzymes have two sites like I said. It has a catalytic site where the substrate is going to bind, and it has an allosteric site where the modifier is going to bind. So this is the active site, and here in this active site, the substrate is going to bind, and here in this allosteric site, what is going to bind? Your modifier or effector is going to bind. Now, if the modifier is an activator, the enzyme will be active. Now, this modifier, it can either be an activator or it can either be an inhibitor. So, either the binding of this modifier in the allosteric site, it is going to enhance the activity of the enzyme, that is enhance the binding of the substrate to the enzyme, or either the modifier can be such that it is going to inhibit the enzyme or inhibit the binding of the substrate to the active site. Okay, so if the modifier is an activator, the enzyme will be active. If the modifier is an inhibitor, enzyme will be inactive. So depending on the modifier, two types of allosteric regulations are there. That is allosteric activation and allosteric inhibition. I hope it's clear. It's really simple. I'll recapitulate it once again. That is, it is trying to say you have an allosteric enzyme which has two sides. One is the active side here, and the other is a different side other than the active side, which is known as the allosteric side. This one here. Okay. Now, in the allosteric side, modifiers are going to bind, and in the active side, substrates are going to be bind. Now, again, there are 2 points. The modifier that is binding in the allosteric side, it can be either a positive modifier or a negative modifier. If it is a positive modifier, it is going to activate the enzyme, and it is a negative modifier, it is going to inhibit the enzyme activity. Now there are, based on the modifier which is going to bind, there are two types of regulation, allosteric activation and allosteric inhibition, okay? And these are terms that you like, you're very familiar and you heard about them very, very often while studying regulation of different pathways. Okay, so talking about allosteric activation and allosteric inhibition. The catalytic site is not favorable for the substrate to bind. Okay. If the modifier is an activator, then it binds to the allosteric site, and unfavorable catalytic site is converted to a favorable catalytic site for the substrate to bind. So this is allosteric activation for you. Let's suppose it is trying to say that this was your enzyme. Okay. This was your enzyme. Okay, and you can see that this enzyme is an active site which is in the form of a somewhat a square, okay? But this is your substrate. The substrate looks like this. So this active site is unfavorable for the start substrate. But what happens? An allosteric modifier is going to come and bind to this allosteric site. You can see this in orange. An allosteric modifier, that is an activator. Okay, so a positive allosteric modifier is going to come and bind in this allosteric site. Now what happens, because of this binding, this inactive site, unfavorable. I should have taken some other shape. Let's suppose it looks something like a star, complementary to a star. Okay. So now your star is going to come and bind. Okay, so this unfavorable side has been changed into a favorable side. Be more clear via the help of the diagram that I've shown you. My picture is not that, the drawing is not that good. Yeah. See, you see, this was the allosteric side. Here an inhibitor. Actually, no. First, we're taking activation. This is the diagram. Okay, so this is the enzyme you see. An activator is going to come and bind to the allosteric site. This is the allosteric site. And what happens when this activator binds to the allosteric site? You can see this active site. It has a very small and shallow groove. And you can see the substrate is so large and huge, like a D. So this was unfavorable, okay, for the substrate to bind. But because of this activator binding to the allosteric site, you can see the change in the active site or the catalytic site. So the active site has altered. This unfavorable active site has become favorable. Okay, so that is the due to allosteric activator or positive allosteric regulation. Okay, allosteric activation. Now talking about allosteric inhibition, here what happens? The catalytic site is already favorable for the substrate to bind, okay? But due to the modifier, which is an inhibitor, when it binds to the allosteric side of the enzyme, not bind. Okay, here. Let's have a look here. What is happening? This is your inhibitor. Inhibitor is going to bind to the allosteric site. And you can see the active site was already favorable. Okay, it is in the form of a huge T, already favorable for the substrate to bind. But because of this inhibitor binding to the enzyme, what happens? This active site has become unfavorable. It has converted into a altered and changed into a small shallow groove, which will not no longer be able to accommodate this substrate in green here. So, okay, so this is allosteric inhibition. So very simple in allosteric activation, what is happening? Because of the activator, your unfavorable active site is going to change into a favorable active site. And in allosteric inhibition, because of the inhibitor binding to the allosteric inhibitor binding to the allosteric site, what is happening? The favorable active site is going to change into an unfavorable active site. Now talking about the characteristics of allosteric regulation. Most of the allosteric enzymes are multi-subunit enzyme possessing quaternary structure. So very important that most of your allosteric enzymes, they are multi-subunit enzymes. Okay, for example, they're going to have multiple subunits. Example, this is one subunit. This is another subunit. This is another. Please ignore my drawing. Okay. So you can see 4 units here. This together is going to form your allosteric enzyme. So basically it is trying to say they have multiple subunits. Okay. So your allosteric enzymes have multiple subunits. That is important. Now what is homotrophic effector? Now we know what is an effector. Effector or modifier, it was binding to the active side. Okay. Oh, sorry. Binding to the allosteric side and bringing about either inhibition or activation. Now, what is homotrophic effector? When the substrate itself serves as an effector, okay? And usually when substrates are acting as modifiers or effectors, they're acting as positive effectors, okay? And you must have also heard this, that substrates usually, when the substrate concentration is more, the reaction is going to run in the forward direction. So substrates are usually acting as positive effectors and they take the reaction forward, okay? Like if there's more glucose or hexokinase is going to be active, something like that. So that is, anyway, what is homotrophic effector? That is when the substrate is going to act as an effector and usually acting as a positive effector. That is homotrophic effector. Okay. And the binding of the substrate. And what is heterotrophic? Before that, let me take this. What is heterotrophic effector? Effector which is different from the substrate. Okay. That is heterotrophic effector. So in this case, your effector is not the substrate, it is some other compound or substance. Okay, so inhibitor. Okay, so that was about heterotrophic effector and homotrophic effector. Homo means same, hetero means different. So when your substrate in itself is acting as an effector and usually a positive effector, it is homotrophic effector. And heterotrophic, well, the effector is not the substrate, it is some other molecule. Now there is another concept which here of cooperativity. Okay, it can either be positive cooperative binding or negative cooperative binding. So what is that? Your positive cooperativity or positive cooperative binding is when binding of substrate to one subunit, like I said, your allosteric enzymes have multiple subunits. Okay, so substrate is going to bind at one subunit of the enzyme, but it enhances the substrate binding by the other subunit. So this is known as positive cooperativity. What is happening? Your substrate is going to bind at one of the subunits of the allosteric enzyme, but because of the binding of substrate to one of the subunits, the binding of the substrate to the other subunits is enhanced. So this is having or known as positive cooperativity or positive cooperative binding. On the other hand, when inhibitor binds to one site, it will inhibit the binding of substrate to other site, and this is known as negative cooperativity. So what are the new terms that we've studied? Homotrophic effector, heterotrophic effector, positive cooperativity, negative cooperativity, and also that your allosteric enzymes are multiple subunit enzymes. So those were 4 characteristics. Moving forward, allosteric enzymes, they do not follow Michaelis-Menten kinetics and instead give a sigmoid curve. And this is because of cooperative effect. Allosteric enzymes, they occupy key regulatory position in metabolic pathways called as key enzymes or rate limiting enzymes. So most of the rate limiting enzymes, they are your allosteric enzymes, and this is how they are regulated. When adding allosteric activator, curve shifts to the left. You can see here. When an allosteric activator, that is positive modifier, is being added, this was the normal curve. So the curve has shifted to the left. You can see here. And when a negative modifier is added, the curve shifts to the right. So that was all about allosteric enzymes, activation and inhibition. Moving on to covalent modification. Okay. So there were two ways how you can control the catalytic activity or quality. One was because of allosteric regulation and the other one was because of covalent modification. So we're done with allosteric activation or allosteric regulation. Now moving on to covalent modification. Now covalent modifications of two types. It can either be irreversible and it can either be reversible. So we're talking about irreversible covalent modifications. It includes partial proteolysis or zymogen activation. Okay. The enzyme is synthesized in an inactive form which has to be converted to its active form before its action. Like we all know trypsinogen, chymotrypsinogen, and all your zymogen activation, basically they are being synthesized in an inactive form. Then because of partial proteolysis or whatever, they are being converted into its active form. So that is irreversible covalent modification, that once activated, they cannot go back to their inactive state again. Okay. So that is your irreversible covalent modification. It is brought about by partial proteolysis or zymogen activation, that is. So the enzymes are being synthesized in an inactive form and then they're being converted into their active form for its action. Your examples are like the digestive enzymes, as I told you, chymotrypsinogen being converted into chymotrypsin. Okay, now this chymotrypsin cannot be converted back into chymotrypsinogen. Okay, so it's an irreversible modification. With trypsinogen being converted into trypsin. Now talking about reversible covalent modification. What is reversible covalent modification? This is addition or removal of a particular group. Okay, so like for example phosphates, for example your acetyls, hydroxylation and all that. So this is you're adding a group and that group can also be removed. That is phosphorylation. That is you're adding phosphate. And when you remove phosphate, it is known as dephosphorylation. And okay, so your hormonal regulation brings about this type of reversible covalent modification. The most common reversible covalent modification is phosphorylation and dephosphorylation. That is addition of a phosphate group or removal of a phosphate group. And this is brought about by hormonal regulation. That is your insulin and glucagon. I've already told you all this. I'm sure you remember your insulin. It was involved in dephosphorylation of enzymes. And your glucagon was involved in phosphorylation. So your glucagon, it was activating kinases because your kinases, they bring about phosphorylation, and your insulin, it was activating phosphatases because they remove phosphate groups from the enzyme. So insulin, it was activating key enzymes of pathways by dephosphorylating them. And your glucagon, it was activating enzymes, activates key enzymes by phosphorylating them. Okay. Now, other groups that can be added or removed, acetyl group that is known as acetylation, ADP, ribosylation, somulation. Okay. So these are all examples of your reversible covalent modification. Most important being your phosphorylation and dephosphorylation, which is brought about by hormones, insulin and glucagon. And your insulin and glucagon, very important. Your insulin, it dephosphorylates key enzymes in the pathways and activates them. And your glucagon, it is going to activate the enzymes by phosphorylating them. And your phosphorylation is addition of a phosphate group, and it is brought about by kinases. Your kinases add phosphate group, and dephosphorylation is removal of the phosphate group, which is brought about by phosphatases. Okay. So your insulin, it is going to activate phosphatases, and your glucagon, it is going to activate kinases. So with this, we come to the end of today's class, that is inhibition of enzymes, the regulation. If you have any queries, you can send them. Okay, thanks for watching. See you in the next class.